Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to our NPTEL online certification courses on engineering drawing and computer graphics. We are covering module number 7 and learning about overview of computer graphics 2. In the last class, we tried to have some idea about these surface models and their construction, especially CAD software uses two basic methods of creation of surfaces. The first one begins with construction of curves from which the 3D surface is then swept or mesh throughout. The second one is direct creation of surface with manipulation of the surface poles and control points. And a computational advantage when people started using these computers trying to use packages, the second method is most powerful, because you will be having isolated discrete points and you try to construct surfaces using different kind of curves through which. And one of the thing what we try to look at in the last classes was, if it is a plane surface, if all your data points lying on one single plane, the easiest way is trying to construct lines across these points and drawing other lines parallelly to that. This is the way one can really construct a surface. And if we are writing it in parametric form, so the background of your or back end of your computer software actually works in that way. It picks isolated discrete points, try to interpolate it and construct surfaces. And at parametric form, if you have point P0, P1 and P2, any new point, perhaps P, one can construct in terms of your P0 point, P1 differencing with P0 and P2 differencing with P0. So, as a reference point P0 we will take, other point is P1, P2. So, we can always construct a plane surface which is passing through these 3 points. 4 points is additional information, but 3 points is good enough to pass a plane. And the normal to the surface, it is not necessary that all these 3 points will be on x plane or y plane, but it can be on different planes. So, through these x, y, z different kind of locations, we can pass a plane. And the surface normal, when you are trying to construct it, will be given in terms of your P1, P0 points, cross product with P2, P0 points and their norms. So, at computer level what it does is, when you are clicking a software like pick this point, that point, another point, it takes these points and your software try to does this interpolation in between those points, try to put a surface. This surface can be plane surface or it can be curved surface. Curved surface construction is bit more complicated and difficult compared to a plane surface. And when we are going to learn about these curved surface interpolations, additional concepts like Bezier curve, Kuhn surface and other things comes. If it is plane surface, it is pretty straightforward approach. The other way of constructing surfaces, it locally looks like plane surfaces, are called ruled surfaces. For example, let us take, I have some curve in 3-dimensional space. Similarly, I have another curve. These curves might be parallel, may not be parallel, they might be offset with each other also. In that case, the easiest thing what one can do is join each and every point, perhaps pick these points, join it by a line. Similarly, pick another point, join it by line. Similarly, pick another point, join it by line and so on. If we are going to construct such kind of object, that is what we called ruled surface. These curves can be arbitrary also. For example, we can have one is a straight line, other one is a curve, and we have decided divide this entire straight line into n number of equal parts. Similarly, the other curve also we are going to divide it into n equal number of parts. Then join each of these things. That represents a simplistic way of looking at a ruled surface, and when you are doing these ruled surfaces, these are always be straight lines, the rule what we have. So, a ruled surface is generated by joining two space curves or rails, is more like trains, the rails what you have, with a straight line ruling or generator. If two curves are denoted by f of u, a parametric variation, and g of u, you can think of this parameter u as a function of time also. With the time, the location of that point moving from one location to another location along a curve, or perhaps you are defining something like it has to go along particular surface like a curved surface. Maybe it might be rolling on a sphere, it might be rolling on an ellipsoid and so on. So, that parametric variation is u, and on that parametric variation we are defining something like a curve, it goes along that the specialized direction, and other curve is g of u. Then the parametric equation at back end of that computer, what it does is you construct any point in between that as some blending functions like 1 minus nu multiplied by g of u plus nu times f of u. It is based on how much distance you would like to really look at, something like the distance between f of u and g of u. If we are representing a fraction in terms of nu, 50% on this side, remaining 50% on that side, or 40% on this side, 60% on that side. That kind of weightage we will apply to really map these two curves by joining a line and try to construct a ruled surface. So, the whole objective at that back end, it goes in this way: you pick lines, you try to smoothly construct a surface passing through these curves. For example, on our computer screen right now, we might be having a curve of that particular shape, and perhaps there is one more line on this edge. Let us consider this is the edge, something like that. Now, I want to really put surface in that at 2-dimensional level. Then how does computer, the one of the easiest way is it picks these data points at pixel level, try to interpolate how I can really join this data point, that data point. So, line by line it constructs it and fills it by particular kind of colors. Same thing happens when you are going to create an automobile or perhaps a pen or any kind of surface. For us at visual level, we feel like the curve or the surface has to pass in that way, but how will you teach it to that machine? The curve has to pass in that way, or the tool bit when you are machining, it has to go along that kind of surface. So, there should be a geometric relation, we have to teach it to these machines or to that computer. And whole objective of any surface model is the best approximation what one can get in terms of constructing a surface. So, based on the curves what we have in 3-dimensional space, we will be in a position to construct a surface joining by these lines, and that kind of surfaces what we call ruled surfaces. So, based on how many data points we would like to construct, one can have a linear interpolation by creating or moving along a specialized directions. one of the easiest way is dividing this line into equal number of parts on both sides and showing one particular arrow direction and try to loft along that surfaces. If we are doing that, we call that as lofted surfaces. In the case of ruled surfaces, it is not necessary that you will have equal number of points on both the sides, but usually for lofted surfaces you divide it equal number of points on both sides of this curve and join by straight lines. So, lofted surface is a specialized form of your ruled surface. The other way of looking at this lofted surface is, for example, we have one particular curve, is a closed curve on one side. We have another kind of closed curve also. Now, there is a line, a spine curve which we call, that is this one. Now, if I really move this curve along that spine curve, whatever the surface it makes, that is what we call lofted surface also. So, this curve, it is a parametric curve. As it is moving from this point to that point, the shape of that curve might be varying. That is the reason what we why we are calling it as parametric curve. Maybe initially at point A, it might be in circular format. At point B, it might be elliptical kind of shape. At point C, it might be having something like a star kind of form and so on. So, we are moving such kind of parametric curve along a spine curve, then also we will be in a position to get a particular kind of surface. That kind of surfaces what we call lofted surfaces. For example, if I am having a circle around certain axis, if I am moving, maybe I might be going to get a tube. The other way of looking at surfaces is revolved surfaces. For example, if I have some arbitrary curve and about an axis, if I am going to revolve it by 360 degrees, perhaps I might be going to get one particular shape. So, a revolved surface is generated space curve about an axis of rotation. So, this is the axis, that is the curve. When we are going to learn about this software package, some of the things like defining an axis, defining curve is important to construct such kind of revolved surfaces. And especially we have some parametric variation r of z in terms of u. In terms of cos functions, sine functions, if I am going to revolve as a circle along one particular z direction, we will get the object which we call revolved surfaces. This always be axisymmetric surface and it can be generated by rotating a plane wire form. Usually, we define positive rotation, something like in counterclockwise direction we will try to rotate the objects. Other surfaces are called tabulated cylinder surfaces. In that case, we have one particular curve. If I am dragging that along particular direction, it forms a surface. That kind of things what we call these tabulated surfaces, and especially a software like SolidWorks, which we will learn it in next classes. There is a command named extrude or extrusion. Using that command, once you draw a curve, you can really sweep it in lateral direction to make the object. Now, where do we use such kind of surfaces? Are there any better way of representing these surfaces? In many applications, if you are looking at like computer visions, like about constructing these 3-dimensional models and so on, or medical imaging, perhaps you might be having a medical imaging thing and you would like to construct 3-dimensional pictures from different views. Is not possible by a human being to really visualize that complicated medical images to construct something like 3D. So, we have to teach it to computer, or perhaps use at least a software which can really read these different views, try to map that, construct the surface. And the back end, what happens is you impose certain mathematical functions which pass through these data points, because we have isolated data points in terms of pixels like colors, red, blue, green, or perhaps white and black, gray scale kind of images and so on. So, we have color contrasts. From there, we will try to impose certain functions, pass curves, surfaces through that to create something like an object. For example, like MRI scan, how the software really construct the 3D images. So, for medical imaging, image generation, surface data is available only in the form of set of data points, and what we all the time interested is constructing that 3D image. And especially most of these softwares work on basic principles like maybe going with Hermite bicubic surface construction procedures, or Bezier surfaces, or B-spline surfaces, something like Kuhn's surfaces which are popular, or Godin surfaces, sudden sharp changes associated with surfaces, something like rounding of surfaces like fillet surfaces, something like chopping of these materials named offset surfaces. So, now we will learn we will have some idea about these surface construction procedure step by step. First of all, we have to define something named curves. Curves are always be single parameter representation. You may be having x as a function of x of u, y might be a parametric variation y as a function of u, z might be function of u. If it is something like a spiral, you have r, theta, phi kind of coordinates which can be connected by one single parameter. In the same way, you have any point x, y, z where you have information, maybe one can pass a curve through that, and that parametric variation what we are saying referring to u. For example, if it is a circle, cos u sin u defines your circle. This u can be theta angular coordinate in one particular instance case, and because it is a circle 2-dimensional thing, so there will not be any z variation. And now I would like to construct something like a curve. I have to join these data points, that means I need something like from one point to other point if I am moving, how that tangent really looks like. First of all, this is the first data point. Unless I know the tangent information, I do not know where exactly the third, fourth, fifth, sixth, seventh points are present. So, all the time I need information about tangent, the point information, the tangent information, so that I can sweep in the next direction to represent something like a curve which can be fit in a smooth way as circle. So, we require that p informations and also we require the tangent informations. If we have, we will be in a position to draw a smooth curve. It is more like on drawing sheets earlier we have tried to draw smooth freehand curves. That is because our visual says that from this point you go in that direction, but to the computer you have to teach construct a tangent, go to next point by integration, maybe it might be Euler integration, go join those things and construct a curve. If it is a surface, we will be having two parameters u and v. Maybe in two directions we will have this parametric variation u v, and any data point on the surface represented by two parameters u v, y is also as a function of u v, z also as a function of u v, and we require partial derivatives describing tangent at those points, like how we talked about a curve, point and a tangent, so that I can really construct a circle. If I would like to construct a surface, first point, second point, perhaps third point, fourth point, these are the points we have. One way is you can always connect by lines, but you want better description. Naturally, you require additional information on the curve has to go downward direction. In that way, the curve has to go upward direction, the curve has to go upward direction and downward direction. Then you will be in a position to really join that by in that way. So, this kind of principle you have to teach it to computer. That means, you require the partial derivatives of that surface which we are describing P of u comma v. You can think of this u v as the new coordinate system on which you are going to draw a surface P, where del P by del u and del P by del v you need to know, or you have to evaluate at that points. So, you might be having 4 data points, but these tangents you are going to map or construct extra, interpolate extra 30 more points in between these 4 points. What is the best way of representing that? That is the whole objective of this surface construction. Some of the essential information what one should really know is about tangent and normals, and what is the range these u and v information one will be having. For example, your space might be from 1 meter to extended to something like 500 meters. But when you are teaching it to the computer, the modules, when you are going to develop or perhaps the background program, you always normalize this 1 500 to something like 0 1 kind of coordinate system. You construct any data point, it is more like a mapping from 1 to 500 to 0 to 1 kind of system. When you do that, you are basically shrinking the same submodule or function, you are all the time calling, these are my x limits, y limits. So, fit a curve in between that, or fit a surface in between 0 1, and again rescale it up to 1 to 500. That is the way it works. If it is a curve fitting, either we will use algebraic relations in terms of linear relations, or perhaps we will be using polynomial functions. For example, a curve x of u, y of u, z of u, the point we have parametric variation. If I am going to fix a polynomial in u, then the curve P is the curve in parametric form, can be written as Ck multiplied by Uk. It is more like the summation k is equal to 0 to n means C1 u1 plus C2 u2 plus C3 u3 plus and so on. How many data points you have, that much. Based on your tangents, you try to derive a relation what might be the weight one has to use for C1, C2, C3 and so on, whether it should be 0.5 times of u1, whether 0.1 times of that or other things. The best example is when we are decomposing a function in terms of sinusoidal, cosine kind of thing by using Fourier series. We always write a0, a1, a2, a3 and so on, b0, b1, b2, b3 and so on, so things. And we try to impose certain kind of condition, what should be that factor a0, a1, a2 and so on, b0, b1, b2 based on the discrete points what we have information. Usually this Fourier series like sine, cosine, we use it for periodic kind of functions, but these data points may not follow a periodic functions. In that case, the best way of approximating these curves is by polynomial expansions. And we minimize, maximize certain kind of weights so that we carefully adjust that everything does by computer, by programs, and finally it constructs a smooth curve along these data points. Similarly, if we are going to construct surfaces, this polynomial expansion we will not only just does in one dimension like x, but we might be going to do it in x y directions or u v parametric variations. So, if we are looking at that carefully, the polynomial surface P as a function of u v represented in terms of your x y z points throughout the space, whatever those discrete points we have, can be expanded in terms of double summation, summation on I, summation on k. It is more like if you are writing a program for I is equal to 1 to or for I is equal to 0 to m minus 1 data points, for j is equal to 0 to n minus 1 data points, evaluate some function c of I comma k multiplied by your parametric u of I multiplied by v of k. That is the way we expand that and try to fix C I informations. And based on my I k kind of information, how many data points I would like to have, I will be in a position to construct a surface. So, some of the important concepts for this surface constructions are: join points for segments and patches, either you join by one point to other point or by patches we will do. The minimum data points what we have, those we will use it like control parameters to make it up and down kind of things, and we require something about tangents, their smoothness also. Based on that information, we will blend the functions to describe the interpolations, and first we will always construct curves and then we will go with surfaces. So, any software what we use, it always involves such kind of step by step interpolations. So, in the next class we will in detail learn about these different kind of surfaces like Hermite, Bezier and other surfaces. Thank you very much.